Now, we have discussed some of the issues with using cascaded multiple higher order filters. Mostly the fact that the transfer function is multiplied, and as it is multiplied, it shifts the cutoff frequency and narrows the bandwidth, or moves the cutoff frequency of a low pass filter to a lower level. And the more filters you cascade together, the more dramatic this effect becomes, as well as the fact that the shape of the knee of the curve from the low passband region to the transition cutoff region is a little bit too gradual sometimes for what we would ideally like to have. So the solution to that, really the only solution, is to go with another type of filter. In your textbook, what is covered is the Butterworth low pass filter. And the Butterworth low pass filter is designed to have a transfer function magnitude of h of j omega that looks like this, which is quite different from the transfer function of the cascaded filter, which I think I have on a previous slide here. I may have to go back a few, but I may have to go back several. Yeah, that looks like this. So this is the one we work with when we have cascaded filter with a prototype cutoff frequency of 1. On the other hand, what we would like to have is, and notice that this has not yet been normalized to 1, so right now we just have some specified omega cutoff. But there's a couple things here about this transfer function that make it very different. First of all, notice that the cutoff frequency is omega c radians per second, independent of the value of n. Because here, when omega is equal to omega c, this ratio is equal to 1, which is 1 no matter what power it's raised to. So independent of the order, if I have this kind of a transfer function, then basically I get 1 over the square root of 2 for my cutoff at the same omega c. Secondly, if n is large enough, then the denominator is always close to 1 when omega is less than omega c. Now, why is this significant? This is significant because as this ratio gets less than 1, we are in the passband region. And of course, a number less than 1 raised to a power gets closer and closer to 1 the higher the power it's raised to. So, or a number that's close to 1 as it's raised to a higher and higher power basically gets smaller. So this is going to be 1 over 1, which means the denominator is close to 1. So as long as omega is less than omega c, and I raise this to a power greater than 1, this number gets small, this denominator approaches 1, and my magnitude of my transfer function also approaches 1. What that means is we don't have as much attenuation and roll-off within the passband happening as early as we would have if we had a cascaded op-amp filter. And then finally, in the expression for the magnitude of h, the exponent of omega over omega c is always even because it's to the power 2n. So independent of the filter order, this would then give you an even exponent. Okay, now how do we get from there to here? Well, if you notice, this transfer function is in terms of j omega. And then remember that S is equal to sigma plus j omega. And we replace sigma plus j omega, we let S go to j omega, we get rid of the sigma, and then we take its magnitude. And in taking the magnitude, we basically are doing an operation that makes it difficult to go backwards from j omega back to S, but that's exactly what we want to do. So what we want to know is what transfer function is a function of S when we substitute j omega and take the magnitude would give us this expression. So in this particular class, because differential equations is a co-requisite and a prerequisite, and because this involves complex number mathematics, which may be in differential equations too, I believe, we're not going to go through the derivation of that. There is a way, given a magnitude function of j omega, to get back to a function of S, and that is outlined briefly in your textbook. But let me just say that basically what happens is you have to consider the fact that since you're taking the magnitude, this j omega terms could be positive or negative. And so that has some repercussions in how you then make substitutions for s. So having said that, basically what we're trying to figure out is for a given value of n, what would the denominator of the transfer function look like in order to give this as our magnitude of h of j omega. So that's where these Butterworth polynomials come from. So first of all, this chart is for a normalized frequency of 1 radian per second. So that's why we went to all the trouble to discuss prototype filters and scaling, is that when you get to more complicated filters like the Butterworth filter, if they're normalized to 1 radian per second, that makes it easier to compare across different filter types and also easier to understand these Butterworth polynomials, which are generated like that. So first, let me say, so n is the order of the filter. So for example, for a second order filter, our transfer function h of s is going to look like 1 over the Butterworth polynomial. What that's going to do is that's going to give us a second order filter. The cutoff region will have a slope of minus 40 dB per decade. The cutoff frequency is normalized to 1. The numerator will be 1, meaning it's going to be a unity gain filter. And it'll have then the transfer function 1 over s squared plus square root of 2s plus 1. For the third order filter, the transfer function will be 1 over this polynomial. For a fourth order filter, it'll be 1 over this polynomial. So if I now take these expressions, any of them, and I substitute j omega for s, and I take the magnitude, what I will get is I will get this expression. So it was a synthesis of the complex frequency transfer function from the expression for the frequency. So that's how these are generated, and that's really all I'll say about that. So notice the polynomial changes for the order. So a couple things to notice. First of all, notice when n is odd, this s plus 1 term always appears. So if you have an odd filter order, one of the stages of your circuit is going to have the transfer function 1 over s plus 1, which is a normal low-pass RC circuit. The other stage is going to be, if we have an odd number, is going to be a different kind of transfer function, meaning we're going to have a different kind of circuit. If n is an even number, then we just have the Butterworth polynomial, we have the Butterworth circuit, we don't have this s plus 1 phase. So that's the first thing to note. The second thing to note is that the constant is always 1. The highest order in the polynomial always has a coefficient of 1. So the main coefficient that's changing is the center term. So that's the second thing to notice. And notice, even for my fourth order filter, I basically have 2 of these multiplied together, and the difference is in the term in the middle. All right, so what circuit generates a transfer function that looks like this? Here is a circuit that provides a second order transfer function for the Butterworth filter. So you have 2 different capacitor values and you have 2 values of R. In your prototype filter, remember we said you wanted as many values as possible to be equal to 1. So in the Butterworth filter, we're typically going to set our values of R equal to 1, but then the Butterworth filter equation is going to fix values for C1 and C2. So in the Butterworth filter, in this circuit, for the prototype circuit, C1 and C2 are not 1, but they're rather determined by the filter polynomial, which I'll talk more about in just a little bit. So equations 1529 and 1530 come straight from your book, and what they basically are is they're node equations. One of the node equations is taken here at V out, and so we have the term V out minus Vn over R, and then we have VA minus V out, and so their inverting and non-inverting amplifiers respectively are VA, or referred to as VA, and since they're equal, they're just referred to as VA. So there's a node equation done here, and there's a node equation done, or sorry, there's a node equation done, and I think I totally said that wrong. This is actually VA right here. That's what they define as VA. This is V minus, this is V plus. These two are equal. The voltage across them is 0. So basically, a node equation is written here at VA. So I have VA minus VI over R. I have VA minus V out over the capacitive impedance for C1. And then I have VA minus V out over R, which is this path. So then I also have an equation written here at the node V out. So here is V out minus VA over R, this path. And then there's this path, which is V out minus V out over SC2. So that's going through here. So two node equations, one written at VA, one written at V out. And then you combine those two because what you want to do is you want to eliminate the unknown VA so that you can get an equation in terms of V out and V in. And when you do that, and then you take V out over V in, this is what you get for the transfer function. Okay, do I expect you to be able to solve that? No. At this point, if writing those node equations is not something that you're able to do, then we're just probably going to have to live with that because at this point we can't really go back over in great detail about that. If you want to go over a little bit more about op-amp circuits and how to write node equations in op-amp circuits, I believe that's covered in your textbook in chapter 5, and they do a pretty good job of explaining how to do that. It's a little bit, it's more of a circuits 1 thing. So if you need help with that, I'm happy to go over that with you. But these are your two node equations, and then this is how you get the transfer function out of the two node equations. There's some algebra in between these two steps that's not shown here. Okay, but here's the important thing. This is your transfer function, and this is what has to look like the the polynomials. So the best way to talk about this is to look at an example. So in this example, this is a 5th order Butterworth filter, because if you come down here to n equals 5, here's your first stage, your second stage, and your third stage. And remember, this is the denominator. So I can actually implement that by cascading 3 filters. One of them is going to be a simple low-pass RC. And it's active. So it's got to be active. You cannot do a passive filter and then 2 active filters to do Butterworth. That's just not going to work. So this is a simple low-pass first-order RC filter. This is a Butterworth filter with this middle term designed to be 0.618. And this is a Butterworth filter with this middle term designed to be 1.618. Where do the 0.618 and the 1.618 come from? They come from the table. Okay, so the table tells you what your design values have to be. Now, the transfer function for the circuit is given here. So the key is to design one of these where these RC1 and C2 values give you 1.618 and 1 respectively, and then to design another circuit with different values of RC1 and C2 where you get these numbers. So in that first circuit, you can see that this numerator, 1 over R squared C1 C2, is going to have to be 1. And so that's here and here. So if you let R equal 1, then that tells you 1 over C1 C2 has to be equal to 1. This middle term tells you that 0.618 has to equal 2 over RC1. So if you let R be 1, then 0.168 has to equal 2 over C1. So that's going to allow you to solve for the value of C1. Once you solve for the value of C1, you know that 1 over C1, C2 has to be 1, so you can solve for the value of C2. So you'll get specific values for C1 and C2 and value of 1 for R. You then repeat that process for this stage of the filter, and you'll get different values for C1 and C2. So you'll actually in total get 3 stage circuits, a low-pass op-amp filter, first order, a second-order Butterworth filter, another second-order Butterworth filter, with the R and C values designed to give you these polynomial numbers. So what's in this equation has to match what's in this equation. What's in this equation has to match what's in this equation, and that'll give you different values of C1 and C2. Now, when all of that's done, you have designed a Butterworth filter with a cutoff frequency of 1 radian per second. So how do you then get a different cutoff frequency? At this point, you will take all of your RC1 and C2 values and you'll scale those using scaling technique, the same scaling technique that we used in the past. First to match your frequency and then to match any component values that you have to meet. In this example, it's a little bit more difficult to meet specific component values on C1 and C2 because C1 and C2 are linked. So you can choose one, but then the Butterworth filter design itself is then going to fix the other. So that's just something to be aware of, that the capacitor values really can only specify what one is going to be, and then that fixes the other because of having to match these numbers and having two different capacitors in that circuit. So that'd be the only difficult thing about actually implementing this circuit is those capacitor values. You don't have any play with one of them once the other one has been selected. Here's another example. This would be a fourth order Butterworth filter. In this case, you see we have two stages of Butterworth filters, and then we have a stage that's setting a gain. So this is just our simple inverting amplifier that's being used to determine a non-unity gain. We would have 4 resistors, preferably all with the same value. Then C1 and C2 and C3 and C4 are designed. Let's go back. Once again, here is our fourth order filter. So then we would be working with 0.765 and 1.848. So the way the fourth order would look like, we would not have this first stage. This stage would contain this number, 0.765, instead of 0.618. And this stage would contain this number, 1.848, instead of 1.618. So that's the design approach on the Butterworth filter. Now, why is this considered superior? Here is a Bode plot comparing two different filter setups. One is the identical cascaded filter, and one is the Butterworth filter. So notice, first of all, in the passband region, the Butterworth filter hugs the gain line a little more closely, and this knee is a little more abrupt. So you have less. In the cascaded filter, you notice we begin to get roll off really a full order of magnitude almost before our cutoff frequencies reach, where in the Butterworth filter it stays much closer to that constant gain. Then notice in the roll-off this transition is much quicker, where in the cascaded filter you have this rounded knee. So what the Butterworth filter does for you, but now notice when you get out here you're still at, in this case, minus 80 dB per decade. But what the Butterworth filter does for you is it makes this knee sharper. And so you're closer to an ideal filter because, go back. You're closer to an ideal filter because you're hugging that constant gain to cutoff, and then once you're in cutoff, you're attenuating pretty rapidly. So you're avoiding this rounded region of the curve that can pass frequencies that you don't want passed and attenuate frequencies that you don't want attenuated. So that's the advantage of using a Butterworth filter.